All right, welcome back to the Explainer. Today, we're unpacking the strict physics definitions of work and energy. We're going to start with the fundamental mathematical tools and build all the way up to one of the most beautiful, elegant principles in all of science, mechanical energy conservation. Whether you're reviewing these concepts or seeing how they connect for the very first time, this is going to make it all click.
So here's our roadmap. We'll start with the math of vectors, move into the physics of work, hit kinetic energy, variable forces, potential energy, and finally wrap it all up with the conservation of mechanical energy. Let's get right into it. Okay, part 1, the math of vectors. Look, before we can even touch physical work, we really have to get a grip on how to multiply vectors using the scalar, or dot product. When you multiply vector A and B, you're not just taking their standard lengths and mashing them together like regular numbers. Instead, you take the magnitude of one vector and multiply it by the specific component of the other that lines up perfectly with its path. It is literally all about alignment. How much do these two arrows actually agree on their direction? That's exactly why we multiply by the cosine of theta, the angle between them. That cosine function beautifully captures that exact degree of alignment. And that alignment? It creates some pretty strict geometric rules. Just think about standard unit vectors, our directional building blocks. If two vectors are perfectly parallel, pointing the exact same way, they multiply together to equal 1. Complete agreement. But if they're perfectly perpendicular, locked at a rigid 90-degree angle, their scalar product is a flat 0. They share absolutely zero common ground. Keep that 0 rule in your back pocket, all right? Because it is the absolute secret to understanding how physical forces actually play out in the real world. Moving on to part 2, the actual physics of work. Now, we really have to draw a hard line between our casual, everyday language and strict physics terms. In everyday life, a student pulling an all-nighter at a desk is doing a lot of work, or a weightlifter holding 150 kilos steady over their head for 30 agonizing seconds, obviously working incredibly hard, right? Muscles are trembling, they're sweating. But physics? Physics doesn't care. In physics, work demands both a force and a displacement. Without actually moving the object from point A to point B, the strict physical definition dictates that absolutely zero work is being done on that load, no matter how exhausted you feel. Which brings us to the classic brick wall scenario. Why isn't pushing against a rigid wall considered work? Well, you can push with all your might. You'll sweat, your muscles are firing, you're burning through a massive amount of internal biological energy. But since the wall itself doesn't budge, since the displacement of that wall is exactly 0, your physical work output is mathematically 0. All that energy was just spent internally. None of it successfully transferred to the wall as work. So the big takeaway here is that work only happens when a force actually causes an object to move, and it depends heavily on that angle we talked about earlier. Work equals force times distance times the cosine of the angle between them. Let's bring back that dot product rule. Imagine a heavy block sliding horizontally across a totally frictionless table. There is a constant downward pull of gravity on it, right? But gravity does 0 work on that sliding block. Why? Because that downward force is perfectly perpendicular to the forward horizontal motion. The angle is 90 degrees. And as our vector math just proved, the cosine of 90 is 0. No alignment, no work. All right, part 3, kinetic energy and motion. There is this incredible, undeniable mathematical bridge between motion and work. If we take a standard kinematics equation, the one relating velocity, acceleration, and distance, something awesome happens when we play with the algebra. But just taking that initial equation and multiplying both sides by half the object's mass, we transform a basic rule of motion into a profound law of energy. Through that simple little tweak, we arrive at the work-energy theorem. It mathematically proves that the final kinetic energy minus the initial kinetic energy perfectly equals the net work done on the object. Work and energy are quite literally two sides of the exact same coin. Which leads us directly to the formal definition. Kinetic energy equals 1/2 mass times velocity squared. And notice, it's a scalar quantity, no direction, just a magnitude. The work you put into a system doesn't just vanish into the ether, it manifests right there as the energy of motion. If you do positive work on a baseball by launching it with your arm, you've transferred energy into it, and its kinetic energy spikes. And because that velocity is squared, the faster it moves, the kinetic energy grows exponentially. Next up, part 4, work by variable forces. Because let's face it, real life is messy. A constant, perfectly steady push is super rare. What if the force changes as you push? Like, say someone is pushing a heavy trunk down a long railway platform and they get progressively tired, so their applied force drops off the further they walk. How do you measure that work? Well, you calculate the total work by slicing the total displacement into tiny, infinitesimally small increments. You find the work for each tiny slice, where the force is basically constant for just a millimeter, and then you just add them all up. Geometrically, this means the total work is exactly equal to the total area under a force displacement curve. And mathematically, we express that massive summation using calculus. Work by a variable force is the definite integral of force over displacement. Why does this matter? Well, it matters because calculus is literally the perfect tool to sum up all those tiny rectangles of work. It proves that our work-energy theorem beautifully holds true, even if the force is fluctuating wildly over the distance. You just sum up the area under the curve, and boom, that total area flawlessly equals your change in kinetic energy. Okay, part 5, understanding potential energy. So potential energy is basically the concept of stored energy. It's energy based on an object's position or its physical configuration. Think about massive tectonic plates deep in the earth acting like compressed springs, storing up unimaginable amounts of energy over centuries until an earthquake finally lets it out. There are two primary types we usually deal with. First, gravitational potential energy. Mass times gravity times height. Hauling a heavy boulder up against gravity, it stores energy in it. Second, spring potential energy. 1/2 the spring constant times displacement squared. Whether you're lifting that boulder into the air or aggressively stretching out a thick metal spring, you are storing energy directly into that system's configuration, just waiting to be unleashed. But here's the catch. This potential energy only exists because of a very special type of force, a conservative force. This is a force where the work done depends strictly on the initial and final positions. It completely ignores the path taken to get there. Gravity is conservative. Spring forces are conservative. The real magic here is that if you move an object in a closed loop, say you carry a heavy box up some stairs, walk around a bit, and then put it right back down on the exact same spot on the floor, the total net work done by gravity over that entire trip is exactly 0. The energy you put in against gravity is perfectly 100% recoverable when the object comes back. And that brings us to part 6, the grand finale, conserving mechanical energy. Let's imagine a solid iron ball being dropped from a high ledge. I want you to track this falling ball like a highly audited, strict financial transaction. We are going to watch it convert the currency of potential energy into the currency of kinetic energy as it accelerates toward the ground. Right at the very top, just before it drops, the velocity is 0, right? So the energy is purely potential. The bank account is entirely filled with height. Halfway down, the ball has lost some of that height, but gained considerable speed, creating a balanced mix of potential and kinetic energy. Finally, right as it smacks the ground at level 0, the height is completely gone, so the potential energy drops to 0. It's now entirely kinetic energy. And here is the beautiful part. While the individual accounts of potential and kinetic energy are constantly fluctuating from point to point during that fall, the total balance sheet, the sum of those two together, remains perfectly, mathematically constant. Which brings us to the core thesis of this whole explainer. The total mechanical energy of a system is conserved if the forces doing work on it are conservative. This elegant, overarching principle means that as long as we can ignore non-conservative forces, like friction or air resistance bleeding energy out as heat, energy in a closed system is never actually lost. It just changes form. It shapeshifts from position to motion and back again, endlessly, in this perfectly choreographed dance. Which leaves us with this final thought. If energy cannot be created or destroyed, only transferred or transformed, where else in the universe can you spot this perfect energy balance? From the elliptical orbits of planets trading gravitational potential for kinetic speed as they sling around the sun, to the absolute microscopic inner workings of an atom, this fundamental rule is everywhere. So I'll leave you to wonder, where else is this incredible law of the universe playing out right now? Maybe even in the objects sitting right there in the room with you. Thanks for joining me on this explainer. Keep wondering and keep looking for that beautiful structure in the world around you.